force. So the force range here is the maximum force range is something around 65, and the minimum we can design by something around 20 piconewton or even less. We can design by changing the base pair combinations. So what they have done here is they have made a patch of DNA, like imprinted DNA, which has different force range, 12 to 15 piconewtons, and now they have allowed cells to grow or stick on this surface. And what they find here is that till 43, so what you see here is mostly dark spots. The white spots here are the cells. Okay. Now you see up to 33 piconewtons, everything is dark, which means no cells actually had stick to the surface. However, from 43 onwards, they started sticking. So which means when a cell comes into contact of a surface, it applies a force which is in the range of 33 to 43. So they have used here DNA as a force sensor. This is recently published in Science. Okay, now what I will do is I will quickly go to my research, which is on hearing, and which is something to do with hearing and balance. Anyway, so what I wanted to show you is okay, this is something about our work in future, or which we are starting now. It's something to do with hearing. So when we hear a sound, what happens is sound wave goes through your auditory canal, and then there's a diaphragm, it hits the diaphragm. So there, the sound wave is converted into mechanical vibration. Right? Now, in the diaphragm, you have three tiny bones, which then creates an oscillation to your inner ear fluid. So as the inner ear fluid now oscillates, as it oscillates, there are inner ear cells. Now, this is an image of an inner ear cell. On top of inner ear cell, you have stereospheres, which are like this. So, if you see, each stereosphere is connected to the with a tiny thread. Now, what happens when the fluid is oscillating, the stereosphere also oscillates, like this way, okay? And with that, we can actually decode sound of different frequencies. So these are the ACM image of stereospheres, and if you see one stereosphere is connected to the longer one with a tiny thread, this portion which is known as tip links. Now this tip link is formed of two proteins, one is known as cadherin 23, another is known as photocadherin 15. So what happens when you have initially when there is no oscillation or no head movement? So if the same thing happens when we move our head, okay, our head, when it tries to balance our body, so it creates oscillation in the inner ear fluid, and then the stereospheres move, and then there is some mechanism underlying. So what happens in the normal case? These are the two stereospheres, and this is the tip link where you have one protein from the top and one protein from the bottom. Just next to this protein, there is an ion channel which is usually closed when it is undeflected. Now, when you have a stimuli coming from sound or coming from head movement, it oscillates the inner ear fluid that bends this stereosphere. So what happens is, now this tip link is stretched, and that acts as a weighted spring. So it opens this ion channel, and now ions can go in, and so that it can change the polarity of the hair cell, and then our nowadays which are at the end of the hair cell can sense the electrical signal very fast and then decode it, reaches to the brain and brain decodes as a sound, right? So the good thing here is that with this mechanism we can actually hear, we can distinguish sound from different frequencies, right? Even though everything is coming at the same time, we can distinguish different sound from different frequencies, and it works all the time without any hysteresis. What it means is, now I am saying something which what you will hear even if I say this is outside or anywhere else. So which means there is no hysteresis. Okay? The way it performed is linear. Now, in order to perform this one, the steep plates should be able to stretch themselves up to 100 nanometer, that too in a repetitive fashion. So it goes and then comes back, goes and comes back, and should be able to stretch them up to 100 nanometer distance. And always it senses a force between 10 to 100 nanometers. So whenever there is a sound, it actually applies something around 10 to 100 piconewton force to the tip links, based on the intensity of the sound or frequency of the sound, which I don't know yet. So these are the hypotheses. Now there is no experimental validation of this thing. So my goal is to understand or to validate those hypotheses experimentally. So the objective here is, first of all, I want to study how strong the bindings are, the binding of these two proteins, and what is the binding kinetics of these two proteins. Then what is the molecular elasticity? What I feel is the molecular elasticity has a very major role to play, because I think it is detecting what frequency of light and sound we are hearing. So I want to study the molecular elasticity also, and then the domain. So what I showed here is the protein looks like this, it has domains, and we do not know what domains are involved in interactions. So I want to study what are the domains involved in this scattering interactions, and then when we have a deafness, or sometimes we momentarily lost our sound hearing, right? If you hear suddenly there is a bomb blasting or something, we momentarily lost our hearing. What happens is the sleep plates get disconnected, but then again starts regenerating. The regeneration happens in a different way. So first we showed that the tip links formed between two proteins, right? Cadherin 23 and photocadherin 15. But when the regeneration starts, only we see photocadherin interaction from both ends. But then eventually the photocadherin is replaced from the upper side, and it is replaced by cadherin 23, and it forms cadherin 23 photocadherin 15. So that is one way where we. I also want to study why that happens. Why photocadherin interaction is not stayed there, instead photocadherin 15 is replaced by cadherin 23. And secondly, we see mutations. What that means is some of the amino acids which form this protein is replaced by some other amino acids, and therefore we lost the connection between these two. And so we have this Usher syndrome, which is like permanent deafness, or that relates to brain diseases as well. So I also want to see what happens when you mutate these proteins and what role they play in deafness. And how do I do that? Again, as I said, as Leta also said, that our work is on single molecule biophysics level, and we use atomic force microscope as well as optical detection techniques in order to study our. So we will use atomic force microscope in order to measure the binding kinetics. So here, what we have is a AFM cantilever, which is coated with one type of protein, and then we have another protein on the surface. So at this stage, we bring them down, we allow them to interact, and then we pull them and hold them at a constant force, and allow them. Now we observe the time requires to unwind or time requires to break the bond. So we can directly measure a lifetime of a bond by doing this way. Okay? So the technique is you allow two molecules to interact and then apply a force and just wait there and see how long they stay there. Okay? And then at some point, because of their intrinsic lifetime at that force, this molecules will break, and you can measure the lifetime of the bond from that way. And then you can eventually get the unbinding kinetics of these molecules. As I said, these two proteins work as a gated screen. So this is just to give you a so which has some role to play. So the elasticity of these molecules has some certain role to play. You can imagine if you use a rope to pull a cell, what will happen is it will actually capture the entire cell, right? Instead of opening a ion channel. So the elasticity of these proteins has to match with the elasticity of the cell membrane. Cell membrane is very soft in order to perform as a weighted spring. So I also want to see the elasticity of these proteins and how do I do that? It's a very simple formula. Just use the spring constant, how you use like two springs in series. But how do you measure that? So what you do is again the same technique. You use AFM. You bring them in contact and now you clamp them at a constant distance. So you measure the distance here, whereas you see the change in the force. So but just by simple F by X using the Hooke's law, you can measure the molecular elasticity of the polymer, right? Let's keep this part. Then also the same way you can measure the domains involved in the interaction. So the number of domains involved, you will see stepwise unbinding from this technique. And then what we get here is we see that how many domains are involved in unbinding and therefore unbinding kinetics, but we don't know which domain is interacting with what or how they are interacting. So here we have hand but no eyes. So we have to introduce eyes here. So what we do is we will, as showed, we will incorporate or we will integrate an microscope by combining atomic force microscope with optical detection. Like we will use some fluorescent microscope and we'll study it, right? So this is a technique where you can resolve the distance between two dyes using 2 to 8 nanometer distance. So you can measure which domains are interacting with what from the fluorescence, and from the AFM cantilever you can measure how much force is required or what combining kinetics and so on. This is the idea here. And as at last, the same thing we can repeat with the mutated proteins. This is overall what we are going to do. Okay, so I'll stop here. I cannot complete my presentation. Yeah.
Are there any questions?